Okay, lesson 101, 101 if you prefer. We are looking at a specific case, which is sine x over x. We're looking at the limit. Our main focus here is looking at the limit of sine x over x for small values of x. So basically, as x approaches 0. Okay. Now, I feel like we talked about this graph at one point. Or am I imagining things? I feel like there was a lesson where we had like 6 graphs, 6 limits at the end, and we talked about it there. So, and we can look at the graph here in a moment too. Thoughts as you look at this? The limit as x approaches 0 of sine x over x. Okay. Could we use L'Hopital's? Okay. So we can use L'Hopital's to prove it to ourselves if we'd like. And why can we use L'Hopital's, by the way? Well, not even just the fact that it'd be over 0, it'd be 0 over 0, right? Because it would be 0 over 0, we can use L'Hopital's rule. And L'Hopital's rule says the limit as x approaches 0. And then what do? We take the derivative of the top. What's the derivative of sine x? Cosine x. Over the derivative of the denominator, derivative of x is 1. So what's the cosine of 0? 1. Over 1. And what's 1 over 1? Equals 1. So according to L'Hopital's, the limit as x approaches 0 of sine x over x is 1. Okay, let's check out the graph. Up there, turned off on me. Depends which spelling you're using.
Well, how did he spell his name?
There's 2 different.
How did he sign it?
I don't know. There's 2 different spellings, so.
Man, wouldn't that be terrible? Where you have to
And
legal
officially-
documents where it wants your full name.
Officially, I think there's a little hat over the O. If you want to get official.
I'm giving the O a hat.
Yep. Okay, so make sure your calculator's in what mode? Radians. Sine x over x. Because it's a trig function, I like to use 7, which is z trig. Does this agree with my answer?
Yep.
The limit as x approaches 0, as they approach 0 from the left, as they approach 0 from the right, we are approaching the y value of 1. Okay, so our plan for the next 2 examples is to not use the calculator and to not use L'Hopital's, but to just know them. Based on the fact, and here's what I'm going to tell you, the limit as something approaches 0 of sine of something over something. I'm not supposed to be putting anything in there. I'm trying to leave it blank. Always equals 1. So I just put a blank set of parentheses each time, trying to show you guys the idea that the limit you need to walk out of here knowing today. Okay, generally if it says the limit as x approaches 0 of sine x over x equals 1. Now, keep in mind there could be slight changes, but the idea is if all 3 of these are the same, it's going to equal 1. Okay, now, so we could say the limit as, how would I think it would still be as x approaches 0, but like 5x over 5, or 5x over 5x it would still equal 1 if those pieces are the same, is what I'm trying to say. Okay? Now, what are your thoughts on example 2?
Well, 4 times 0 inside is going to be 0, so I'd say it's just like the top.
But if you did the multi-house thing, you'd have 1, 4.
Explain.
So
Wouldn't it just
I'm
be,
kidding. Yes, explain.
Wouldn't it just be 4?
Yeah. Maybe it's just be
4
4.
would be 1/4 cosine of 4x. So it'd be 1/4 times 1. I'm just doing like the multi-house thing.
But when you take the derivative, you don't do fractions.
Oh,
You
yeah.
take the derivative of the whole function, then you take
Yeah.
the derivative of the
We've
inside.
been doing too many integrals. Yeah. Here it is.
Okay, yeah, I was waiting for, yeah, you were trying to compensate and doing an integral, but we're just doing a derivative. And so, okay, so, yes, this does equal 4. Now, the idea is, why does it equal 4? Because there's this 4 in front of the x right there. Okay, notice everything else about it, sine x over x, it's still the same idea. L'Hopital's is your proof. If you're wanting proof, and you guys already went there and talked about it, so the limit as x approaches 0, derivative of sine x, sine of something, is cosine of something times the derivative of something. And the derivative of 4x is 4 over derivative of x is 1. And so that is where we would have cosine of 0 is still 1, so you end up with 4 over 1, which is 4. Okay? And again, it's all about learning to recognize them without actually doing L'Hopital's. Before we do L'Hopital's, guesses on example 3.
147.
Actually, I wasn't even going to necessarily do L'Hopital's now that I think about it, but I can. 1 over 47. And you can think, I guess maybe you could do L'Hopital's, obviously, right? For the same reasons as above. You can also look at the fact that, okay, if this was upside down, the limit as x approaches 0 of sine of 47x over x. Well, based on what we just learned up above, that would be 47, correct? So if you flip it upside down, it's going to be 1 over 47.
Oh, I just forgot to put the 4 in front of the cosine on my page on the previous example.
Okay. And you're like, wait, how did we get that?
Yeah.
Okay. So we did look at this graph previously, didn't we? Did you find the spot, Daryl?
I didn't see this one. I saw the 6 graphs, but this wasn't.
This wasn't one of them? Okay. So either we haven't looked at it or we looked at it someplace else and I'm just not remembering where.
It's probably someplace else. 'Cause I feel like I've seen it.
We did sine of 1 over x there, didn't we? We've used it someplace. I agree. I don't remember where. So, okay. Questions on the top part there. Your goal is to just recognize it and not have to work it out. Now, the good news is we've showed you can just work it out, right? Okay. Ready for a proof? Of course you are, right? We're going to prove the derivative of sine x. To prove the derivative of sine x is cosine x, we only have to prove that the limit as x approaches 0 of 1 minus cosine x over x is equal to 0.
That's easy.
That's easy?
Yeah, sure. I'll go with it. Sounds good right now.
Okay, so starting with, what is it? The limit as x approaches 0 of 1 minus cosine x over x. And we're not going to talk L'Hopital's. I'm going to take that out of the equation. They're out of the scene here. So, I guess what I need to say is the whole idea is we're going to use the information we have from up above. The fact that the limit as x approaches 0 of sine x over x is 1. We're going to use that information. Okay? Now, to get to there, we're going to use a technique. Multiply by a conjugate. What's the conjugate of 1 minus cosine x? And whatever we do to the numerator, we're going to do to the denominator. So we're going to multiply numerator and denominator of this fraction by 1 plus cosine x over 1 plus cosine x. So when we multiply, it's still the limit as x approaches 0. What do we get when we multiply on top? Okay. When we FOIL these, it would be 1 minus cosine squared x. What about your denominator? There's two ways we can put it. We do not necessarily have to distribute it. And yeah, I did not distribute in my notes. If you distribute it, it'd be x plus x cosine x, which I think we'd end up having to undistribute eventually. So I'm just going to say x times 1 plus cosine x. Okay? Equals the limit as x approaches 0. The thoughts on that numerator? What did he say? Sine squared x because? One of the Pythagorean things. Does that make sense to everybody when he says that? Pythagorean identity, sine squared x plus cosine squared x equals 1, right? So manipulate it. My pre-calcs have been doing this. 1 minus cosine squared x becomes sine squared x. So now I have sine squared x over x times 1 plus cosine x. Now, based on the fact that I said we're using, whoops, I forgot my parenthesis there. We're using the information up above. The fact that the limit is sine x over x equals 0. What do you see within this problem? Or do you see it? Do we have a sine x over x here?
Yeah.
We have a sine x over x here, don't we? So I'm going to rewrite this limit where I'm going to separate the insides into two fractions. So if we make one of the fractions sine x over x, we know what that limit is going to equal, right? Times, now, what's within the other fraction if I'm separating this into two fractions?
Sine x over 1 plus cosine x.
Yeah. It was sine squared on top, so if I put sine x on one fraction numerator, sine x is on the other one. Denominator, I've already pulled the x aside, so that means this is 1 plus cosine x. Now, officially, I'm doing proper notation here. If we go back to limit rules, which I have to say it correctly here, the limit of the product is equivalent to the product of the limits. Right now, this is the limit of a product and is equal to the product of the limits, which means I can break this into two separate limits. So I can say the limit as x approaches 0 of the first fraction, sine x over x, times, and then we can repeat the process, the limit as x approaches 0 of my other fraction, which is sine x over 1 plus cosine x. What do you know about that first limit?
Equals 1.
One of the things you're supposed to walk out of here knowing today is the limit as x approaches 0 of sine x over x is 1. Okay. What about the limit as x approaches 0 of sine x over 1 plus cosine x? Can we do that yet?
Maybe plug in 0.
Yeah, if we plug in 0, it works now, doesn't it? So sine of 0 is 0 over 1 plus cosine of 0, 1. Although what is 0 over 1 plus 1? 0. And what is 1 times 0? You got him then. Good job. He's making sure you're awake. You've caught up on sleep. Okay, 1 times 0 is 0. What was our goal to prove? That it equals 0. Okay? And we did just that. Okay, so one of, numerous ways that you will, you could see the sine x over x. So just, again, walk out of here knowing limit as x approaches 0, sine x over x is always 1. You put a multiple in there, it's going to multiply to be whatever that number is. You flip it upside down, that answer is going to be flipped upside down. So just some helpful pieces there to work with. And this comes in play when you don't have a calculator, right? You don't have the graph, yes, you can still use L'Hopital's, but you have to be careful, you do that. So this comes into play then. Before I forget, I've written down that 19 becomes 9 from 93, and that you are skipping 7 and 8.